Today we're going to have a look at topic 6, right triangles. Okay, first let's have a look at the concept of right triangles. A right triangle is a triangle that has a right angle among its angles. The side opposite the right triangle is called the hypotenuse. So this side is hypotenuse. And the other two sides are called legs. This is a leg, this is another leg. In the figure to the right, for example, AB is a hypotenuse, while AC and BC are both legs. As you'll see throughout the book or this course, many problems are solved by building right triangles and using the principles we have already learned in this chapter or in this topic, particularly one of the most famous math theories of all, called Pythagorean theorem. So let's have a look at the Pythagorean theorem here. The right triangle ABC has hypotenuse AB equals C, and legs AC equals B and BC equals A. Use similar triangles formed by altitudes CD to prove that A squared plus B squared equals C squared. So probably you have already know the Pythagorean theorem, right? If you have a right triangle, A is a leg, B is another leg, C is a hypotenuse, then we have A squared plus B squared equals C squared, right? So the problem is, can you prove this is actually true? Well, actually, there are a lot of ways we can prove the Pythagorean theorem. Here is one of the methods. So note that in triangle ADC, we have angle A equals angle A in triangle ABC, right? And this angle here plus angle A equals 90 degrees. We also know this angle here plus angle A equals 90 degrees, right? So we could say because angle A equals angle A, angle DCA equals angle ABC, right? Then we know triangle ACD is similar to triangle ABC, right? And this means we have B over E. Well, this side is E. This side is, that's called AD equals E, BD equals D. So B over E is C over B, right? Therefore, we have B squared equals EC, right? And similarly, we can show that because angle B equals angle B and angle BCD equals angle BAC, we have triangle BDC is similar to triangle BCA, right? Therefore, we have corresponding sides are proportional. So A over D, A is here, over D should equal C over A, right? And this gives us A squared equals CD, right? Therefore, we know A squared plus B squared, just insert EC and CD here. EC plus, CD plus EC. And C is a common factor, so put it in front. That means C times the sum of D plus C. Sum of D plus C is actually C, right? So that's actually C squared. You see that? So here's one of the many methods we can prove the Pythagorean theorem. Of course, you can also think of another ways. Did you get it? And in a summary, in any right triangle, the sum of the squares of the legs equals the squares of the hypotenuse. If you have a setup like shown here on the right, then a squared plus b squared equals c squared. This is called famous Pythagorean theorem. Did you get it? Any questions? Okay, so let's use the theorem to do a little exercise here. You find the missing sides in the triangle below. 1, 2, 3, 4. We have 4 triangles here. I'll give you 1 minute to solve these questions, okay? Okay, again, when you finish, please give me your answer in the chat box, okay? All right, let's have a look at the solutions together. Okay, according to Pythagorean theorem, so look at the first triangle. If you don't know that side, you can always let it to be x, right? So this means we have 8 squared plus x squared equals 8 squared root 2 squared, right? So 64 plus x squared equals 64 times 2. Therefore, x squared equals 64. We know x must be positive, so x equals 8, right? So BC equals 8. For the second triangle, okay, note that we want to find this side, EX. So you can use triangle EXF. EXF is a right triangle. Therefore, we can find this side first. So if you know this side is 10, this side is 6, using 10 squared minus 6 squared, you can find EF squared, right? So EF squared is 100 minus 36, which is 64. And EF is 8, right? And then EX squared is 17 squared minus 64. And 17 squared is 289. Minus 64 gives you 225. Well, if you're familiar with this number, you know the square root of 225 is actually 15, right? So EX is 15. So this side is 15. Okay, next one. This is pretty straightforward. So you have a right triangle. You know the hypotenuse. You know one leg. The other leg is just square root of 14 squared minus 7 squared. So this is, well, you can put 7 squared in front, right? Then what's left in the parentheses is just 2 by 2 is 4, right? Minus 1. So immediately you should know that 7 square root 3. Did you get it? Of course, you can also calculate 14 squared first, minus 49. But in that way, you will get a number square root of 147. So usually we'll simplify this number to 7 square root 3, right? So you could do it either way. And last one, you know one leg, the other leg, the hypotenuse equals square root of first leg squared plus second leg squared, which is square root of 9 plus 64, which is square root of 73, right? Okay, any questions? Okay, good. Then let's consider another quick quiz. Suppose we have an isosceles triangle MON, in which MN equals 7, NO equals 7, MO equals 10. Can you find the area of MNO? Okay, be careful how you write your solution, okay? You need to make your reasoning legit. Okay, have you finished? Okay, let's have a look at the solution together. So a pretty simple thought is, if you want to find the area of a triangle, you should know the base and height, right? So suppose we use MO as a base, then you need to know the altitude or height in that base. So for example, we can draw, let's say this point is A, draw MA perpendicular to MO at point A, right? Then we know MN equals NO. We also know, therefore we know angle M equals angle O, right? Because we also know angle NAM equals angle NAO. Then triangle NAM is congruent to triangle NAO, right? Therefore, we know MA equals OA, which is 1/2 of MO, which is 5. This side is 5 and this side is 5, right? And in right triangle NMA, we can find MA because according to Pythagorean theorem, MA is just square root of MN squared minus MA squared, right? So this gives us 49 minus 25, which is square root 24, which is 2 square root 6, right? And if you know the altitude and you know the corresponding base, it's easily to find the area of M and O, which is 1/2 of MO times NA, which is 1/2 of 10 times 2 square root 6, which is 10 times square root 6, right? Any questions? Okay, so this is just one application of the Pythagorean theorem. Okay, let's get back to Pythagorean theorem. This Pythagorean theorem states that if you have a right triangle, then we have a squared plus b squared equals c squared, right? So the question is the reverse statement is also true? Which means, for example, if you have a triangle, one side is A, the other side is B, and the third side is C. If you know a squared plus b squared equals c squared, can we conclude that this triangle is actually a right triangle? This is a reverse statement, right? Well, it's not necessarily true before you prove it, right? So can you prove that is true or not? Okay, let's have a look at this question. So the question is, suppose we have a triangle ABC such that BC equals A. Okay, suppose you have a triangle like this. A, B, C. BC equals A. AC is B, and AB is C. And we know A squared plus B squared equals C squared. Question is triangle ABC necessarily a right triangle? It seems like it's a right triangle, right? But how can you prove this is actually true? Okay, let's have a look at the solution together. Well, actually, we can draw another triangle. So we can draw EF equals A, right? This is possible, right? By using only a compass and a straight edge, we can draw EF equals A. And we could also draw a line that is perpendicular to EF, make this angle be 90 degrees, right? Also, we can draw DF equals B. This is also possible, right? Then we connect E and D. So according to Pythagoras theorem, we know in this triangle is a right triangle, right? One leg is A, the other leg is B. So the third leg must, let's call it X. So X squared must equal A squared plus B squared, right? And we know A squared plus B squared equals C squared. This is according to the given information, right? Therefore, we know X must equal C. Can you see that? So if you consider triangle EFD and triangle ABC, we have EF equals BC equals A. We have FD equals AC equals B. We also have ED equals AB equals C, right? Therefore, we know triangle EFD must be congruent with triangle okay, let's find the corresponding vertices. So if this is hypotenuse, it should be BCA, right? EF equals BC, FD equals AC, ED equals AB. Yeah. So according to SSS, right? Because we have three pairs of equal size. According to SSS, these two triangles must be congruent with each other, right? Therefore, we know angle ACB must equal angle DFE, right? Which is 90 degrees. So this angle here must be 90 degrees. Did you get it? Therefore, we have proved the reverse statement is actually also true, right? Okay, let's make a summary here. So this means if the size of the triangle satisfies the Pythagorean theorem, then the triangle must be a right triangle. Anytime you see a triangle size that satisfies the Pythagorean theorem, you should mark the angle opposite the longest side as a right angle. You get it? So in a summary, when you have a right triangle ABC, suppose hypotenuse is C, then we will have C is hypotenuse. We know that A squared plus B squared equals C squared, right? And the reverse statement is also true, which says that when you have A, B, C are three sides of a triangle, if you have A squared plus B squared equals C squared, then we know this is actually a right triangle. Did you get it? All right. No questions? Let's have a look at a quick quiz here. So the side lengths are marked in the diagram on the right. Can you find the length of CD? Okay, have you finished? Okay, note that it looks like we have a right triangle, right? But it does not say so. So if you want to use any right triangle, you need to prove that angle is actually a right angle. So note that we have this side is 3, AB is 3, BC is 4, and AC is 5. So we know 3 squared plus 4 squared equals 5 squared, right? Which means AB squared plus BC squared equals AC squared. Of course, you don't have to write it here. You could write it on a scratch paper. Because of this, we know triangle ABC is a right triangle and AC is hypotenuse. So angle ABC is 90 degrees, right? And triangle BCD is also a right triangle. It's also a right triangle. And CD is hypotenuse, right? Therefore, according to Pythagoras theorem, we have CD squared equals BC squared plus BD squared, and this gives us 16 plus 81, which is 97. Therefore, we know CD equals square root of 97. We cannot simplify that, so you can just leave it there, right? Alright, next let's have a look at two special right triangles. Okay, let's use an introduction problem to illustrate the concept here. So triangle XYZ is an isosceles triangle as shown with angle Y equals 90 degrees. Given that XZ is 6, can you find angle X and the length of XY? Again, when you finish, please give me your answer in the chat box. Okay, have you finished? It's pretty easy to find the angles and the set lines, right? Because we know the sum of these three angles equals 180 degrees. And this is isosceles triangle, so if you let this angle be theta, then this angle is also theta, right? So we have 2 theta plus angle y equals 180 degrees. Therefore, we know theta equals 90 degrees over 2. So that's 45 degrees. And if you let this side be x, then this side is also x, right? According to Pythagorean theorem, we have x squared plus another x squared, which is 2x squared equals this set squared, which is 36. Therefore, we know x squared equals 18, and x is 3 times square root 2, right? So this problem suggests that we might be able to find a general relationship among the sides in an isosceles right triangle. So in a summary, in any isosceles right triangle, the legs are equal and the hypotenuse is square root 2 times the leg. So why is that? Because if you let this side be x, this side be x, then, for example, if you let this side be y, then we have x squared plus another x squared equals y squared. Therefore, y is square root 2x, right? So this is a relationship between the hypotenuse and the legs. Therefore, you can use this as a theorem. Because angles of isosceles right triangles are always 45, 45, and 90 degrees. An isosceles right triangle is sometimes called 45, 45, 90 triangle. So if we know the length of any side of such a triangle, we can quickly find the others using the side relationships shown in the figure at right. Okay, you should put this down on your notebook. Any questions? Okay, and this is one of the two special right triangles we're looking at. And next, let's have a look at another special right triangle in which we have 30, 60, and 90 degrees internal angles. So how are the sides of a triangle that have angle measures 30, 60, and 90 related? For example, if the length yz is x, what is xy and what is xz? You find them? Okay, have you finished? I'll give you some hints. Okay, if you see the angle 60 degrees, then probably we can use the property of equilateral triangles, right? So how about we extend the y to another point A, for example, such that ya equals yz. This is possible by using straight edge and compass only, right? And then connect xa. Then we have ya equals yz, right? And this angle is 90 degrees, this angle is another 90 degrees. And they share the same length here, right? And because angle AYX equals angle ZYX, and of course XY equals XY. So this tells us the left triangle XYA is congruent to the right triangle XYZ by SAS congruency, right? You find that? Therefore, we know angle AYX equals angle YXZ equals 30 degrees, right? Therefore, this angle is 30 degrees, this angle is 30 degrees, and we immediately know this angle is 60 degrees, right? Therefore, angle AXZ equals angle XAZ equals 60 degrees, right? And if this angle is 60, this angle is 60, this angle is 60, then this triangle is equilateral triangle, right? Therefore, we know XA equals AZ equals ZX equals X, right? So this side is X, this side is X. You get it? So if you know this side is, 2x, my bad. This is a 2x, 2x, and 2x, right? Okay, then if you know this side is x, this side is 2x, so according to Pythagorean theorem, xy is square root of xz squared minus yz squared, right? Which is 4x squared minus x squared, which is square root 3x. Can you see that? So this side is square root 3x. Did you get it? Okay, so the takeaway is when you have a right triangle whose internal angles are 30, 60, and 90, the ratio of each side is x over square root 3x over 2x. If you divide both sides using x, so that's actually 1 over square root 3 over 2. That's the relationship between the legs and hypotenuse. Did you get it? Okay, let's make a summary. So in a right triangle with acute angles of 30 degrees and 60 degrees, the sides are in the ratio of 1 to square root 3 to 2, as shown to the right. Such a triangle is often called 30, 60, 90 triangle. So far we have learned two special right triangles. One of them is 45, 45, 90. The other one is 30, 60, 90. If you know the ratios, if you know the two special ratios, you should quickly find the relationship between the three sides, right? Did you get it? Okay. Do you have any questions? Okay, if not, let's do a quick quiz using what we have learned so far. Okay, can you find all the missing sides in the diagram, which means this side, this side, this side, and this side, and this side?
Is the 30 degrees in triangle ABC angle BAC?
Yes, okay. Angle BCA.
BCA, sorry.
Okay, you need to find AC, BC, CD, CE, and CF. Okay, I'll give you a hint. Okay, we have learned two special right triangles. One of them is 45 degrees, 45 degrees, 90 degrees. In this case, the ratio of each side is 1 to 1 to square root 2, right? The other one is 30, 60, 90. In this case, ratios are 1 to 1 to square root 3 to 2, right? Okay, first of all, we can find the length of BC, right? Triangle ABC, if this angle is 30 degrees, note that the hypotenuse is always twice of the side that is opposite to the smaller acute angle 30 degrees, right? So if this side is 6, we should know this side is 12, right? And then how about this side? This side is square root of 144 minus 36, right? Which is square root of 108. Then that is 6 square root of 3, right? This is one way to find the other leg. And if you are familiar with the ratios of the legs, you could also use the ratio of the legs. We know that the longer leg is square root 3 to 1 of the other shorter leg, right? If the shorter leg is 6, we should immediately know this leg is 6 times square root 3, right? Then always check your answer by using the Pythagorean theorem. This side squared plus this side squared will give you this side squared, right? Therefore, we know AC is 6 square root 3, BC is 12. So how about CD? So in this special triangle, it's 45, 45, 90, right? We know the hypotenuse is always square root to 1 of the leg, right? Therefore, if you know this leg is 12, then this leg is also 12, right? Then the hypotenuse is always square root 2 times the leg. So we have 12 times square root 2 for CD. Of course, we can also find BD equals 12. And then consider the special right triangle CDE. We know one leg, CD is 12 square root 2. Well, if you let this side be x, then the hypotenuse EC is 2x, right? You don't have to memorize that using brutal force. So if you let D equals x, EC then is 2x. Then we have 4x squared equals x squared plus CD squared, right? CD squared is 12 square root 2 squared. Then you can find a equation in terms of x. 3x squared equals 144 times 2, right? So x squared equals 48 times 2. So x equals, okay, 48 times 2 equals 96, which is so you have 4 times square root 6, right? So here this side is 4 times square root 6, and this side is 8 square root 6. Can you see that? So DE is 4 times square root 6, and CE is 8 square root 6. And last, we need to find EF and CF, right? Again, you don't have to memorize using brute force. If you don't know that, you can always let it to be an x. Then this side is also x, right? Therefore, you have x squared plus x squared equals EC squared, which is 8 squared root 6 squared. So 2x squared equals 64 times 6, right? X squared equals 64 times 3. Therefore, x equals 8 square root 3, right? Can you see that? Therefore, we know CF is 8 square root 3. And also EF is also 8 square root 3. You get it? Again, do not memorize using brute force. I'll give a hint here. We have learned two special right triangles, right? One of them is 45 degrees, 45 degrees, 90 degrees. And if you let one leg be x, the other leg must be also x, right? So according to Pythagorean theorem, this side is square root 2x, right? And in the other special right triangle, we have 30 degrees, 60 degrees, and 90 degrees. So if you let the shortest side be x, then hypotenuse is always 2x, right? Then again, according to the Pythagorean theorem, we know this side is square root 3x. You get it? Okay, any questions? No? Alright, then let's have a look at another concept which is called Pythagorean triples, which is quite straightforward. Pythagorean triple is a set of three integers that satisfy the Pythagorean theorem. For example, 3, 4, 5 is a Pythagorean triple because we know 3 squared plus 4 squared equals 5 squared, right? However, 1, 2, 3 is not a Pythagorean triple since there's no way to add two of the three numbers to get the third number. Did you get it? So this concept is called Pythagorean triples. Okay, then let's consider another quick quiz. A, can you find the missing side lengths in each right triangle shown below? B, consider given that ABC is a Pythagorean triple, is twice of A, twice of B, twice of C also a Pythagorean triple? How about NA, NB, NC, where N is any positive integer? Okay, let's have a look at the solution together. For the first one, if one leg is 3, the other leg is 4, then we know the hypotenuse is 5, right? Because 3 squared plus 4 squared equals 5 squared. So how about the next one? 10 squared minus 6 squared equals 64. Then the other leg must be 8, right? So how about the next one? 400 minus 16 squared is 256. That'll give you 144, right? So this side must be 12. Can you see that? Okay, you can actually use a calculator to find the hypotenuse of the last one, right? So what is the length of the hypotenuse here? Okay, let's just leave it aside. So can you see some pattern here? Originally you have 3, 4, 5, right? If we enlarge each side by a number 2, by a factor 2, then you will have 6, 8, 10, right? If you enlarge the original size by a factor of 4, you will have 12, 16, and 20. They still form a Pythagorean triple, right? So it's probably when you add a integer in front of each number, the new three numbers is still a Pythagorean triple, right? So can you actually prove that? Yes, of course we can, right? So we know ABC is a Pythagorean triple, and let's check NA, NB, NC. So what is NA squared plus NB squared? NA squared plus NB squared is actually N squared A squared plus N squared B squared, right? If you put N squared in front, you will have N squared times A squared plus B squared. We know A squared plus B squared is C squared, right? So that equals NC squared. Can you see that? Therefore, NA, NB, and NC is also a Pythagorean triple, right? Which means originally, if you have a Pythagorean triple ABC, and you enlarge each of the numbers by a factor of n, where n is a positive integer, then the new numbers NA, NB, and C are still a Pythagorean triple, right? So here, this number is 3 by 111. This number 444 is actually 4 by 111. So as you can see here, we have just enlarged each number here by a factor of 111. So we know that the hypotenuse is the number 5 enlarged by a factor of 111, right? So that's 555. So you don't have to use a calculator to find the hypotenuse. Well, actually, the n does not have to be a integer, right? Suppose it's a real number, then we still have something squared. Then the new numbers NA, NB, and C is also a Pythagorean triple. You see that? For example, if n equals 1 over 7, then the new three numbers are 3 over 7, 4 over 7, and 5 over 7, right? We can still prove that first number squared plus the second number squared equals the third number squared. Did you get it? Therefore, the takeaway is if A, B, C are the sides of a right triangle, then so are N, A, N, B, and C for any positive number n. For example, if we know 435 is a Pythagorean triple, then we know all of these numbers are Pythagorean triples as well, because we simply enlarge each of the numbers of the Pythagorean triples by the same factor, which is a positive number. Did you get it? This is a property of the Pythagorean triple. You should know, okay? Alright, then let's see another important property of the Pythagorean triples. I'll use this example to illustrate this concept. So can you find the last side in each right triangle shown on the right side? And do you see a pattern? Can you prove the pattern always works? Okay, let's have a look at solution together. For the first one, we know the hypotenuse is 5, right? For the second one, we know this side must be 8, according to Pythagorean's theorem, right? It's easy to find the other number. So this number here is 17. So how about this one? This one must be 10, right? And this leg is 37 squared minus 12 squared, then square root, which you will get 35, right? So if we make a table, first column is the smallest even leg, and second column is the other leg. The third column is hypotenuse. Then let's see if we can identify some pattern there. Okay, for the first triangle here, if the smallest even leg is 4, the other leg is 3, and hypotenuse is 5. And for the second one here, if the smallest even leg is 8, the other leg, the smallest even leg is 6, the other leg is 8. And the hypotenuse is 10. And for the next one, the smallest even leg is 8, then the other leg is 15. The hypotenuse is 17, right? And for the next triangle, smallest even leg is 10, the other leg is 24, and the hypotenuse is 26. And for the last one, the smallest even leg is 12, the other leg is 35, the hypotenuse is 37. So can you find any pattern there?
I don't know if this is a pattern, but like the other leg plus the hypotenuse is always can always divide the smallest even leg, and it's like twice and then triple and then times four times and then five times and then 6 times.
Not quite. Does it work for any of the triples?
Like 3 plus 5 is 8, and it's 2 times 4, and then 8 times 10 is 18, is 3 times 6, and then 32 is 4 times 8, 50 is 5 times 10, and then 72 is 6 times 2, 12.
Yeah.
I don't know if it's a pattern, but
Yes,
it's just...
yes. You can think of this question like this, and actually we can summarize this. If you have 2n, then this number here can be written as n squared minus 1, right? And the hypotenuse can be expressed as n squared plus 1. So that's why n squared minus 1 plus n squared plus 1 always equals 2n squared. Right? Can you see the pattern here? So basically, if you can express one leg using 2n, then we should immediately know the other leg must be n squared minus 1. And the hypotenuse is n squared plus 1, right? So why is that? Because you can check this by using the Pythagoras theorem. 2n squared plus n squared minus 1 squared will give you 4n squared plus n to the power of 4 minus 2n squared plus 1. And this can be simplified to n to the power of 4 plus n 2n squared plus 1, which can be written as n squared plus 1 squared, which means this is a hypotenuse, right? Okay, and this is also a property of the Pythagorean triple. You can use this as a theorem. Okay, did you get it? All right, then let's have a look at let's revisit congruence and similarity. So congruence and similarity also applies to right triangle. So let's see this example here. Are the two triangles shown congruent? Why or why not? Remember, we have several ways to determine whether two triangles are congruent or similar, right? So basically we have this side equals this side, right? And this side equals this side. And we have a pair of equal angles here. But we have S, S, A, right? Usually when you have a triangle that yields SSA, SSA does not necessarily mean congruence, right? But if this is a right triangle, do we have a congruence here? If it's a right triangle, SSA does work, right? Because you can easily find AB and GF, which is square root of 100 minus 81, which is square root 19, right? This side is again square root 19. Therefore, actually we have SSS, right? So by SSS, we have a pair of congruent triangles. Did you get it? Therefore, we could say triangle ABC is congruent to triangle FGE by SSS, right? So normally by SSA, you won't have a pair of congruent triangles, but if you have a pair of right triangles, SSA could mean actually SSS, and SSS tells us a pair of congruent triangles, right? Okay, and let's have a look at another property that is related to the congruence of right triangles. So can you prove that if radius OC, so suppose we have a circle which is centered at O here. OC is a radius. Can you prove that if radius OC of circle O is perpendicular to the chord AB of circle O, then radius OC actually bisects chord AB. Bisects means this side AX should equal this side XB. Can you prove that? Again, seems like we can use a pair of congruent triangles, right? So in this case, we know this angle equals this angle. Both of them are 90 degrees. And OB equals OA, right? OX equals OX. You see that? So we could say because AO equals BO, XO equals XO, angle AXO equals angle BXO equals 90 degrees. So do not use, again we have SSA here, right? So do not say SSA indicates congruence. You need to prove AX equals, okay, AX equals square root of AO squared minus XO squared, right? And BX equals square root of BO squared minus XO squared. Therefore, we know AX equals BX, right? So we have proved AX equals BX. Can you see that? AX equals BX, not because SSA, but because we have a pair of right triangles, and two pairs of the equal size indicates the remaining pair of sides are also equal, right? Okay, any questions? Okay, again, you can use this conclusion as a theorem. So next time, when you have a setup like this, if OC is perpendicular to the chord AB, okay, suppose you have a chord here, and this is a radius. If the radius is perpendicular to the chord AB, then you should know this side equals this side in a circle, okay? You can use this as a theorem. Okay, in a summary, if a radius of a circle bisects a chord of a circle, it's perpendicular to the chord. Conversely, if a radius of a circle is perpendicular to the chord, it bisects the chord. We have already proved the later statement. You can figure out a way by yourself to prove the first statement. Actually, the reverse statement is also true. Okay, again, you can use this as a theorem in your future lessons. Again, you don't have to write everything down. I'll give you my notes after this class. You can also review the lecture slides from YouTube channel, okay? But you need to comprehend this theorem by yourself. Alright, then let's have a look at a quick quiz. So it tells you the center of a circle is 4 units away from a chord of the circle. If PQ is 12, what is the radius of the circle? So suppose we have a circle. Center of a circle is 4 units away from a chord PQ. Well, let's say this is a PQ. And we know this length is 4, right? And we know PQ is 12. What is the radius of the circle? So you want to find the radius, so probably we'll connect PO and OQ, right? You need to find OP or OQ. That's the radius of the circle. Okay, so according to what we have learned previously, we know when, let's call this point M. We know when OM is perpendicular to a chord PQ, then we should immediately know this length equals this length, right? So if PQ is 12, this length is 6, this length is 6, right? And in right triangle PMO, we know PO should equal square root of PM squared plus MO squared. And this gives us 36 plus 24, which is square root 60. Oh, sorry, MO is 4, so that's 16. So that's square root of 52, right? And we can simplify that to 2 times square root 13. So that's the radius of the circle, right? Can you follow me? Okay, so we have just finished the congruency, and next let's have a look at a question that involves similar triangles. So in the diagram here, are the two triangles similar? Why or why not? We have AA similarity, SAS similarity, or SSS similarity that can be used to determine whether two triangles are similar, right? So if you want to use, seems that we can use SAS, right? So if you want to use SAS or SSS, well, if you want to use SAS, you need to know the length of AB, know the length of RQ, right? Because this is the angle in between, not this side, right? Okay, so first of all, you can find the length of AB. So length of AB equals square root of length of BC, BC squared minus AC squared, which equals square root of 225 minus 144, which is square root of 81, and this is 9, right? And RQ equals square root of PR squared minus PQ squared, which is 400 minus 256, which is square root of 144, and this gives us 12, right? And then you need to check whether the corresponding sides are proportional. So you can check AB over, seems that AB over RQ is 9 over 12, which is 3 over 4, right? And AC over PQ is 12 over 13, which is also 3 over 4. That equals AB over RQ, right? And we know angle A equals angle Q. The angle in between also equal. Therefore, we have triangle ABC is similar to triangle QRP, right? By SAS, not by SSA. Remember, SSA does not necessarily mean similar, right? Do you get it? Of course, you can also use SSS to check similarity, right? If you know the three sides, if the three sides are all proportional with each other, then by SSS, you can also prove they are actually similar. Okay, and one last piece of information. The Heron's formula. In the triangle ABC, if we let AB equals C, AC equals B, and BC equals A, and let S equals half of the perimeter of this triangle, which means half of the sum of ABC, can you find the formula for the area of ABC in terms of S, A, B, and C? Okay, which basically means you know the length of ABC, and can you find a formula for the area of ABC using A, B, and C? Any thoughts? We'll give you 3 minutes to have a look at this question, okay? And we'll have a look at the solution together after that. Okay, I'll give you a hint. When you want to find the area of a triangle, usually we'll use 1/2 of its base and corresponding altitude, right? So suppose I draw a AX that is perpendicular to BC and denote this side as H. Then of course the area of this triangle is just 1/2 of H times A, right? So can you find the length of H? Of course we already know A here. Can you find the length of H? Alright, let's have a look at the solution together. Actually, it's not that easy, so we'll have a look at the solution together. Okay, so if you want to find length of h, we can use the right triangle ABX or AXC, right? So suppose we let BX be x and let XC be a minus x. Of course, that's a minus x because we know BC equals a, right? So in this case, we have x squared plus h squared equals c squared, right? Did you get it? And we also have, if you use a right triangle, you have a minus x squared plus h squared equals b squared, right? So this is a system of two equations, and we have actually only two unknown quantities, which is x and h, right? So we should be able to find the values of x and h using these two equations. Basically, it's an algebraic problem. You need to find x and h by giving a system of two equations like this. Okay, seems that we need to cancel one of the variables, right? If there is only one variable, it's very easy to solve. So intuitively, we can use equation number 2 minus equation number 1, right? And this will cancel h. Or you could also use equation number 1 minus equation number 2. Doesn't matter, right? Equation number 1 minus equation number 2 will give you x squared minus a minus x squared equals c squared minus b squared, right? So we can expand that. If you expand that, you will get x squared minus a squared minus 2ax plus x squared equals c squared minus b squared, right? And then reorganize that. And luckily we can cancel x squared here, right? So that'll give you negative a squared plus 2ax equals c squared minus b squared. And it can easily solve that x equals a squared plus c squared minus b squared over 2a, right? Of course, if you solved x, then just insert x in either of the equations. You can easily solve h, right? So apparently the first one is much easier. So let's put equation number 3 into equation number 1. And this gives us, okay, first of all, x squared. Okay, we want to find h squared. Okay, let's not do this because when you want to put that here, that expression is very complex. So let's start by looking at equation number 1. So from equation number 1, we have h squared is c squared minus x squared, right? And let's lower the power number here. So this is c plus x times c minus x, right? And now you can put equation number 3 to equation number 4, which gives you h squared equals c plus x is c plus this expression here, right? So c plus a squared plus c squared minus b squared over 2a times c minus x, which is c minus this expression. Not that bad, right? Then that equals, the first expression is 2ac plus a squared plus c squared minus b squared over 2a, right? Second expression is 2ac minus a squared minus c squared plus b squared over 2a, right? Can you see that? Okay, I'll continue writing at the top, okay? That equals, first one can be simplified to a plus c squared, then minus b squared, right? Over 2a. Can you follow me? Our second expression is b squared minus a minus c squared over 2a. Right? Okay, again, you can expand the first one. So again, you have expression like something squared minus another thing squared, so that equals a plus c plus b times a plus c minus b, right? Over 2a times, second one gives you b plus a minus c times b plus a, sorry, b minus a plus c, right? Over 2a. You follow me? And that'll give us a plus b plus c times a plus c minus b times b plus a plus b minus c times b plus c minus a over 4a squared, right? Okay, let's erase this. Okay, note that we are given s equals half of a plus b plus c, right? So we know we can express that a plus b plus c is 2s, right? A plus c minus b. A plus c minus b is 2s minus 2b. Can you see that? Because 2s is a plus b plus c. The minus 2b gives you a plus c minus b. Can you see that? And using the same method, we can also rewrite a plus b minus c. A plus b minus c is 2s minus 2c, and last one, b plus c minus a is 2s minus 2a, right? Over 4a squared. Then that can be simplified to, okay, in this case we have 4s, s minus a, s minus b, s minus c over a squared, right? Can you see that? This is the length of h. Remember, we are trying to find the length of h. This is the length of h, right? Therefore, the area of triangle ABC is given by 1/2 of h times a, right? So insert your h here. This gives you 1/2 of 4s, s minus a, s minus b, s minus c over a squared times another a. Then we can cancel something there. Cancel a 2 will give you 2 here. Cancel an a will give you a here, right? Oh, sorry, my bad. I forgot. This is actually h squared, right? So let's rewrite these. Okay, that's actually h squared, not h itself. So triangle ABC equals 1/2 of BC times h, and this is 1/2 of BC is A. That's, can put A here. That's 1/2 of A times h, right? H is square root of 4s times s minus A times s minus B times s minus C over A squared, right? And then that's A over 2 times. We can put A squared outside the square root sign. So that's 1 over A times 4 can also be put outside there. So that becomes 2 here, right? Times square root of s times s minus A times s minus B times s minus C. So eventually we'll cancel these. So that gives us square root of s minus A times, sorry, square root of s times s minus A times s minus B times s minus C. You see that? So that is the area of that triangle in terms of S, A, B, and C. We know S, A, and B, and C. Right? So the takeaway is, when you know the three sides, you should be able to find area of that triangle. So please put this on your notebook. This is called Heron's formula. This formula tells us that if the sides of a triangle are A, B, and C, and if you let S denote 1/2 of the perimeter, or 1/2 of A plus B plus C, then area of the triangle can be calculated by square root of S times S minus A times S minus B times S minus C, right? Okay, so that concludes our lesson today. I'll give you my homework. Give you the homework and notes to Google Classroom. You can download from there. Okay, I'll see you next time. Bye.